and direction. In other words, if I was to represent two vectors with arrows, these two arrows would need to be equal in length and pointed in the same direction or parallel in order to be equal vectors. Now there's one important exception to the rule that a vector must have both a magnitude and direction, and that is the zero vector. A zero vector has a magnitude of 0 and a direction or no direction. That's why it's the exception. It has no direction, because really I could be pointing 0 units in any direction. So we have no direction for the zero vector, and I'm going to show you in the next slide why we need to define the zero vector in the first place. Let's take a look at these two vectors, vector AB and vector BA. We see that they're equal in length and that they're parallel, but these two vectors do not equal each other. They do not equal each other because they're pointed in different directions. In fact, they're pointed in exactly opposite directions, which makes these two vectors negatives of each other. In other words, vector AB is equal to the negative of vector BA. And we get negative vectors by multiplying one of the vectors by a -1 or a scalar. We're going to talk about that more in another video. But effectively, if I multiply one of these vectors by -1, I switch the direction or flip it 180 degrees, and therefore I get the other vector. Now, just like with any two numbers that are negatives of each other, if I add them together, I get 0. So 2 and -2 are negatives of each other. Likewise, if I add vector AB and vector BA, which I know are negatives of each other based on the diagram, I'm going to get 0. And we're going to talk more about vector addition in the next video. But just keep in mind that just like with two numbers, when I add negatives together, I'm going to get 0. Let's take a look at an example problem. Here we're given parallelogram ABCD, and by definition, opposite sides of a parallelogram are parallel and equal in magnitude. We're also given that vector AB is equal to vector A. And vector BC is equal to vector B. In this problem, we're asked to find expressions for vector BA, vector CB, vector AD, and vector CD. And we're going to use the properties that we've discussed in this video to find equivalent expressions for these vectors. So let's take a look at vector BA. First thing we notice is that it's equal in length to vector AB and exactly opposite in direction. Well, if vector AB is equal to A, but I'm talking about the negative vector, then vector BA is equal to negative lowercase a. Likewise, vector CB is the exact opposite or negative of vector BC, which we know is equal to B. So therefore C must be equal to negative B. Vector AD, notice, is parallel and equal in magnitude to vector BC. Well, if BC equals B, then AD must also equal B, or vector B. And the last one is vector CD, which is equal in length and opposite in direction to vector AB, or vector A. So again, this is equal to the negative of vector A.